All right, so if you guys could be quiet, that'd be fantastic. Thank you. Today we're doing lesson 8. And if you are watching this later, tomorrow, which is your today, obviously you are finding the recording here, which doesn't exist yet, but the what's it called? Replays of the various YouTube videos made from code are going to be available in our Google Slides so that you can watch them on a Chromebook, since you can't get to the regular YouTube on Chromebooks. So we have this nice, lovely workaround. And before I forget, we'll do keyboard shortcuts of the day just to catch up. I think we did Control Scroll before. Hold down Control, and scroll wheel up and down is zoom. Control Shift or Control with click on a list, which if you ever see two vertical bars in computer science, two vertical bars means or. And in this case, if you're on some list in some Finder window, you probably know you can hold down Shift and click and it gets everything in between, but you probably don't know that if you hold down Control, you can click non-sequential ones and then handle it that way. That's super useful. Control Shift T is reopen the last closed window or last closed tab, and Control Shift L, R, or E, left, right, or center for justification. So Control Shift L, left justify, Control Shift R, right justify, Control Shift E, center, and that works on anything. All right, so lesson 8, color images. We are now using our bits for something else other than numbers or letters or black and white images. Obviously, this is a lot closer to black and white images. Let's put this up on the big screen. But obviously, it's more complicated than just black and white images or black and white pixels. So we now have one bit or a number of bits for each of 3 different channels. And you've probably heard red, green, blue before, RGB. It is always going to be in that order: red, green, and blue. And we use bits to decide or define how much of each, how much red, how much green, and how much blue a single pixel should have. Okay, and let me see if I can find, I don't know why the video is not popping up. It's probably because I've already been here today. And so there's a couple like 2 or 3 minute videos that we will get through. Let's copy this and go like this, copy. And okay, so this first video is just half of it's an introduction to binary, which we've already have. Wow. Sorry. But the second half is how it will apply to us here. Okay, there we go.
Hi, my name is Lenora Free, and I'm an engineer here at Adafruit Industries. And this is where I do engineering and design, and I design circuits for fashion and music and technology.
My name is Federico Gomez Suarez, and I'm a software developer with Microsoft Acronym. And I look into using technology to help us solve key social problems at times.
You may have heard that computers work on ones and zeros, or you may have seen scary looking visuals like this. But almost nobody today actually deals directly with these ones and zeros. But ones and zeros do play a big role in how computers work on the inside.
Inside a computer are electric wires and circuits that carry all the information in a computer. How do you store or represent information using electricity?
Well, if you have a single wire with electricity flowing through it, the signal can either be on or off. That's not a lot of choices, but it's a really important start. With one wire, we can represent a yes or a no, true or false, a 1 or a 0, or anything else with only 2 options. This on-off state in a single wire is called a bit, and it's the smallest piece of information we can store. If you use more wires, you get more bits. More 1s and 0s with more bits, you can represent more complex information. But to understand that, we need to learn about something called the binary number system.
In the decimal number system, we have 10 digits from 0 to 9, and that's how we've all learned to count. In the binary number system, we only have 2 digits, 0 and 1. With these 2 digits, we can count up to any number. Here's how this works. In the decimal number system we're all used to, each position in a number has a different value. There's the 1 position, the 10 position, the 100 position, and so on. For example, a 9 in the 100 position is a 900. In binary, each position also carries a value, but instead of multiplying by 10 each time, we multiply by 2. So there's the 1st position, the 2nd position, the 4th position, the 8th position, and so on. For example, the number 9 in binary is 1, 0, 0, 1. To calculate the value, we add 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Almost nobody does this math because computers do it for us. What's important is that any number can be represented with only 1s and 0s, or by a bunch of wires that are on or off. The more wires you use, the larger the numbers you can store.
With 8 wires, you can store numbers between 0 and 255. It's 8 ones. With just 32 wires, you can store all the way from 0 to over 4 billion. Using the binary number system, you can represent any number you like. But what about other types of information, like text, images, or sound? It turns out that all these things can also be represented with numbers. Think of all the letters in the alphabet. You could assign a number to each letter. A could be 1, B could be 2, and so on. You can then represent any word or paragraph as a sequence of numbers. And as we saw, these numbers can be stored as on or off electrical signals. Every word you see on every web page, phone, is represented using a system like this. Now, let's consider photos, videos, and all the graphics you see on the screen. All of these images made up of teeny dots called pixels, and each pixel has a color. Each of the colors can be represented with numbers. When you consider that a typical image has millions of these pixels, and a typical video shows 30 images per second, now we're talking about a lot of data here.
Every sound is basically a series of vibrations in the air. Vibrations can be represented graphically as a waveform. Any point on this waveform can be represented by a number. And this way, any sound can be broken down into a series of numbers. If you want a higher quality sound, you will pick 32-bit audio over 8-bit audio. More bits means a higher range of numbers.
When you use a computer to write code or make your own app, you're not dealing directly with these 1s and 0s, but you will be dealing with images or sound or video. So if you want to understand how computers work on the inside, it all comes down to these simple 1s and 0s and the electrical signals in the circuits behind them. They are the backbone of how all computers input, store, process, and output information.
Okay, so we are now going to use bits in a different, more advanced way. Like I said before, we now get 3 different colors. Hold on a second. There's actually another short video introduction in a second. For each well, 3 different colors for each pixel, and we say how much of each color goes into that pixel. Here we only have 1 bit per pixel, so it's either all the red or none of the red, and so on. And we're going to use that in the color widget, which is, here we go, part 1. This is quicker. There we go.
In this version of the widget, we've made setting the metadata of the image a bit easier. For the width and height, you can type the decimal numbers you want, use the sliders, or type the binary as you did before. It's useful to be able to change these things quickly to see the effects on the image. Notice when you change the data by typing or using sliders, the binary data changes and the image canvas reflects the changes. There's another piece of metadata here called bits per pixel, which will allow us to make more than purely black and white images as we did before. To see what it does, let's set bits per pixel to 1, which is what we had for black and white images before. And let's paste in the familiar black and white image. In order for a pixel to have a range of colors, it seems logical that we will need several or many bits to represent the color of each pixel. The bits per pixel setting in the metadata tells the widget how many bits it should use to calculate the color of a pixel. You can see if I change the bits per pixel setting, the widget will interpret the bits differently, and you'll see some colors start to appear. Of course, the binary data for this image was written for a black and white image with 1 bit per pixel. But if we change how that data is interpreted by increasing the bits per pixel that the widget is expecting to see, the image gets garbled. Let's start over and try to put that thing.
Okay, so what's happening there is by changing the slider, you're changing the chunk size that the computer is expecting. And so those 1s and 0s are useless at that point when it's chunking it off by different amounts.
This image was written for a black and white image. Increasing the bits per pixel that will try to get the hang of using color in digital images. I'm going to make a very small image so that we can really look at what's happening with the pixels. So I'm going to set the width to 4 and height to 2. Now let's look at how RGB colors work with this tool. As you know, for color images, each pixel is actually a combination of red, green, and blue light. If we want to represent that in binary, the least we can do is allocate 3 bits for each pixel, 1 bit each for the red, green, and blue values. I can use the slider to set the number of bits per pixel I want to use to render the image. So I'm going to set the bits per pixel to 3. So now, I will get the color black. And if I turn all the lights on, I get white. Since I have 1 bit of control for each of the red, green, or blue lights, I can turn them on and off individually. So if I want a red pixel, I can turn on the red light and turn the green and blue lights off. So that's red on, green off, and blue off. 1, 0, 0. And presto, I get a red pixel. Now you keep going and create a green and a blue pixel. Notice that when we have 3 bits per pixel, the first bit controls the red light, the second controls the green light, and the third controls the blue light, R, G, B. Now it gets interesting. What happens if we mix the lights? Let's see what happens if we turn on the red light and blue light and leave the green light off on the same pixel. Before I type it, make a mental prediction. What color do you think we'll get if we mix red and blue? Think about it for a second. All right, ready? Here we go. Red on, green off, blue on. It made pink.
All right, so clearly this is not pink. Clearly this is purple. Now, why is it purple and not pink? Well, this may be your first introduction to the concept of color correction. And that is, depending on how your device is adjusted, it may make a slightly different shade of the color that's intended. It's not a big deal. Almost all of the time, human eyes sort of adjust to it There are keys and clues that your mind can pick up on, like the color of grass will adjust in your mind what you're actually seeing, but it's not a critical issue unless, say, you're dealing with some sort of brand that has a very specific color of, one of the colors. Okay, so that's a thing. But the takeaway is that this is that combination of red and blue makes a purpley
Is
pink
that what
color.
you predicted? I'm guessing that you thought it might be purple. Well, this is one of the key differences between mixing light and mixing heat. It's actually the opposite physical process. When you mix a lot of heat together, the color gets darker and darker. When you mix a lot of light together, the color gets brighter and brighter. It can take some getting used to, but you'll get the hang of it.
Okay, so light has what's called additive properties, meaning the more colors you put in, the brighter it's going to get, because you're adding red light and blue light to a green. It's going to make it brighter green. It sounds it's counterintuitive again. Pigments have what's called subtractive properties. The more paint you put together, the darker it gets, and that's why it always ends up at brown or some sort of whatever color. So we'll get to later on the ability to like actually create custom colors just from your understanding of how the light works. But for now, we're just looking more for patterns in the binary.
With only 3 bits, we know that I can only combine them 8 different ways. So with 3 bits, only 8 colors are possible. Now you keep going and finish the remaining 2 colors.
Okay, so go ahead to code and open up bubble 2. When you get here, you will notice a couple of things. I think we could probably do this a little quieter so we're listening. Here we go. Let's go ahead and do this. Excellent. Okay, so as you saw in the video, we now have an extra slider, the bits per pixel. And as you change the number of bits per pixel, you'll notice that over here on the right, the pixel format readout there will change from black and white to color. It will only be color at very specific amounts of bits per pixel. Who can figure out what all the ones that are colorful have in common? Any guesses? Which amounts of bit per pixel are colorful? What do you got, Daniel? Well, no, because 11 bits is black and white, but 9 bits is color. Yes. Oh, no, I don't have one. What do you got? It is multiples of 3. That is because in order to have a red, green, blue combination, you have to have the same number of each. Okay. And in this case, we are starting with just 3-bit color, which is the lowest multiple of 3. And in this case, that means with 3-bit color, we have 1 bit for each color. So with 1 bit, we only have 2 options, off or on. And so if we wanted a red, our only amount of red we can give is all of the red, and then none of each of the others. If we wanted pure green, our only option for green is either 0 or 1. And so 1 gives us a green with 0 red and 0 blue. And if we wanted a blue, we would have 0 red, 0 green, and blue would be on. Okay, with 1 bit per pixel, each red, green, or blue is either on or off. Now, one of the takeaways from this entire lesson is that we can now use bits some other way than just making numbers. These first 3 bytes, the first 24 bits are the metadata, the data about the data. They are not the colors of the pixels. They are telling the program how big the canvas is and information about the bits that will follow. And these 3 bytes, these 3 8-bit chunks are translated as numbers, but the next bits are just amounts of color. Okay, this is not the number 4. 100 is 4 in binary if you're converting to decimal, but in our pixelation widget, 100 in this case is just for this first pixel, how much red, how much green, and how much blue. Okay, so these are the only 3 combinations with only one of the colors turned on. Okay, and there are 3 combinations with 2 of the colors turned on. So red and green on, blue off makes yellow. Red on, green off, blue on makes magenta. Red off, green on, blue on makes cyan. And then the only other combinations you can make with 1s and 0s is all 0s and all 1s. Those are the 8 different colors you can make with 8 bits. Okay, and these are not in any order. They're not in any order. They're just colors. If you wanted to do them in order of, if you're trying to convert these into these 3-bit numbers into like in order, it would be 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so this is 0 through 7 if you were converting, but that doesn't tell us anything. That's not in any particular order. Okay, these colors aren't in, they're not in like rainbow order or darkest to lightest, because these aren't numbers insofar as the way we use numbers. Okay, so that's it for bubble 2. Let's go on to bubble 3, which is a diamond bubble, so it is informative. All right, so if we are using 6 bits per pixel, that's 2 bits for each color. That means each color can have a range from 00 to 11. Okay, with 00 being the lowest, 01 the next, 10 the next, and 11 the most. That means we can have 4 different values for each, which means we have 4 different options of red values from no red to all red. But it means we have 4 times 4 times 4. We can make 64 different colors with 2 bits per pixel, but that's not our goal here. Our goal here is on the next bubble to come up with you're given the 6-bit combinations for the on the red scale, as we would call it, from the darkest red or no red, which would be all black, to the most red, and so on. Okay, your job is to come up with the equivalent for green and the equivalent for blue. Okay, I'll give you a hint. I'll just do the green one. Okay, the lowest green would be 00, and we're keeping red and blue off. The next amount of green would be 01 with red and green off. Next amount would be 10 with red and blue off. And the next amount would be 11 with red and blue off. Okay, we'll call that, I guess, the green scale. And the last one is blue, which would look like that. Okay, I don't know if any of y'all saw that little shortcut. But go ahead and do that. Okay. So because being clever and finding easy ways to do things is just as valuable as understanding this, you'll notice that because we're doing things in order of red, green, and blue, the second most or second least amount of red is 0, 1. And in the next row, our second least amount of green is 0, 1. So in the next one, the last 2 bits for this pixel would be 0, 1. So all this is, if you put 0, 0, and then pasted the entire thing from the last row down, it's the same. So yeah, that's a clever way of doing that, which is only applicable in this one particular case. But there you go. Okay, next one. Same thing, except 3 bits per color, which is 9 bits per pixel, which I think there's a video for it, but maybe it's from the last one, maybe it's for the next one. I don't know. But I think hopefully you're getting the gist of it. Here we are going through each combination of red with 3 bits of red options, with the lowest being all of the red off and the highest being all of the red on. Which leaves us with the range from all zeros, then 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. Every possible combination of red with green and blue off. Okay, that's what you've been given. Okay, so the next row is every possible combination of green with red and blue off. So it's always going to be, and I probably could have done this before, a different amount of green in the middle here. So if I go like this, okay, the lowest amount of green is would be 0, 0, 0. I don't know if this is the best way to explain it. The next lowest amount would be 0, 0, 1. The next lowest amount would be 0, 1, 0. The next lowest amount would be 0, 1, 1. And no, wait, 0, yeah, 0, 1, 1. Is that right? Did I mess it up? Oh yeah, good call. Yeah, this is not the best way to explain it. 0, 0, 0, 0, 1, 0, 0. Let's just go readable format, make it less bad. 0. Well, either way, there remains the trick. Like that. Okay, so that is the order for these. Shouldn't be too terribly difficult. Let me see if I can find that other video from. Is this one critical? Yeah. All right, so if you guys can keep it down, I won't make you stop what you're doing, but this other video, please feel free to pay attention. By keep it down, I mean like silently down.
So that's the basics of RGB color. Now, of course, you're asking, how can I make more in different colors? Well, the answer is that we must use more bits per pixel. Let's get rid of the image data we just created, and then change the image to be 4 pixels by 4 pixels, and 6 bits per pixel.
Oh, is that the one we just did? Oh, never mind. This is the one from 2 ago. All right. Anyway, let's do, okay, so that's it for bubble 8. Or excuse me, bubble 5. Let's go on to the next one. Okay, so this one is very reasonable, except for the fact that you are supposed to choose one of these 4 images, and you are going to use this app over here, which this complexity of app in App Lab is like a day 1 app. You will all be making much more complicated apps than this pretty quickly. But the way it's used, you hit run, and then you have access to drop downs that do different things. Okay, the first one is a drop down of the 4 different images that you can choose to sample. Excuse me, to sample. And the second is how many grids you would have to sample. And if you recall from yesterday, the difference in number of grids affects, pixelation, that sort of thing. So of these 4 images, the only one I see any value in getting or in using is image 2. And the reason for that is they're either so complicated, well, the other ones to do well would be a incredible level of complexity, and also not necessarily possible. This grayscale one, I mean, I guess you could go through and pick out the different grayscales, which we will talk about in a second. Actually, we'll talk about right now. But the number 2 actually seems useful, where if you chose a grid that had a like either 2 or 3 rows, you can see that there's a nice clear delineation where it's that dark pink purple, then a light version of it, then a light yellow and a dark yellow. And if you did medium high, it would be 6 rows. So you'd have 3 of the pink increasing and then 3 of the yellow decreasing. I would recommend doing either one of those. The problem is that the place you're supposed to create this is in bubble 7. So you don't have access to your sample in App Lab. The best way to do this is to right click on, well, if you're in bubble 6, right click on bubble 7 and vice versa, if vice versa, and open in a new tab. So now you can have bubble 6 in one tab, bubble 7 in the other tab, and you can drag one to the side and do a nice split screen situation where your sample is on one side and your would-be canvas is on the other. And there actually is sort of enough room there. So here is something to notice. Let's talk about grayscale for a second. This is an important concept. So as you drag the bits per pixel, you can see that the only colorful ones are the ones that are multiples of 3. There is no situation in which you will use, or any software uses, a number of bits per pixel that isn't a multiple of 3. And, well, because you want color ability to make colors. Okay. So the trick is, how do you make gray using colors? Well, the lowest, let's just do 6. Let's do 9 bits per pixel, so that's 3 of each. Okay, I will give you, okay, we know black is 0 red, 0 green, 0 blue. Okay. I have not enough. There we go. Okay, we know white is all of the red, all of the green, all of the blue. Okay, I'll give you a couple gray tones, a couple gray scales, and see if you can figure out the correlation. If I had 4 for red, 100, for green and blue. Am I not doing enough zeros? 1 0 0 1 0 0. Oh, okay. There's one gray color. How about there's another gray color? How about okay? What do these grays have in common? Anybody? Who can see a comment? What do you got? If you have the same amount of red, the same amount of as green and blue, it will be on the grayscale. All the way from black, which is the same amount of each being none, to white, which is the same amount of each being all. That is how you make a grayscale color, is the same of each. Okay, you can't make a grayscale with 3 bits per pixel because your only options are 3 bits per pixel. Your only options are all off or all on. So you would need at least 6 bits per pixel to have options for a certain amount of red, a certain amount of green, and a certain amount of blue. That would give you grayscale. Okay, so back to what we're trying to do here is if you have both tabs up at the same time, it would be pretty useful. And what I'm going to teach you here is a bit of a useless party trick, and that is being able to guess a color either from binary or from decimal. And guessing a color's number is sort of the same trick as coming up with the number for a color you're trying to create. And the key is starting with a known value. And it is counterintuitive that if you have pure red, so let's say, let's just do a nice big 1 by 1. So, or maybe 2 by 1. If you have pure red, which would be, and we're doing 9 bits in my example here, if you had, come on, computer, all the red, no green, no blue, that's pure red. The way that you make light red, also known as pink, the way you lighten a color is you add more light to it. We're already at maximum red. How do you add more light to it? Well, you actually have to add green and blue to it. Sounds like, why would you add green and blue to something to make it brighter? Well, more, let's say, okay, so we're still maxed out at red. Let's add a medium amount of green and a medium amount of blue. Okay, that is a lighter version. It's not a great example. Let's try a slightly mediumer amount of each. Okay, so here we've gone from full red, no green, no blue, to full red, 0, 1, 1 green and 0, 1, 1 blue. And we've lightened it up. We can light it up more by doing, how about, what's the next one? 1, 0, 0 green and 1, 0, 0 blue. Okay, we're adding green and blue to something that's red to make it brighter red. It sounds counterintuitive until you start thinking about it as light. Okay, you're adding more light to it. If you add the same amount of the other two, which theoretically you'd add the same amount to all 3, but we're already tapped out in this case for red. If you add more light to it, it will brighten it. Okay, that is the counterintuitive nature of this. So if we are trying to recreate this one here, we really just need to come up with 4 different colors and do a full row of this dark magenta, or just regular magenta, a row of the light magenta, a row of light yellow, and a row of dark yellow. Okay, so if we're doing it this sample size, we have it 6 wide and 4 tall. So let's make it 6 by 4. And our magenta, if we're doing 9 bits per pixel, that will give us 8 different options for each of the 3 colors. What was magenta? That was red and yellow? No, wait, red and blue. So that's 111, 000, 111. Okay, so let's do a whole row of that. And how about readable format? There we go. So how are we going to make a lighter magenta? Well, we need to add light to it. We can't add any more red or blue. We're already at the top. So we need to add more green. Even though this is not a green color at all, the only place we can add light is from green. So how about we have to keep full red? How about what's right in the middle? 100 of green, and full blue will give us this lighter magenta. I would even go one lighter. So the middle 3 should be 101. There we go. That's a pretty good color. And I need 6 of those, 5 more. Okay, then I need 2 other colors. I do know yellow. Yellow, let's go with this full rich yellow is going to be full red, full green, and blue off. Okay, but it's a little darker than that. So how do we go darker than that? Let's take light away. We can't take anything away from blue, but we can take it away from the other 2. So how about 110 for red and 110 for 110 for red, 110 for green, and still nothing for blue. And I need 1 more. There we go. That's pretty good. There's not really any more. Maybe I can add 1 to the blue to brighten it up. Yeah, it's not too bad. Let's go 0, 0. Okay, and I need a lighter version of this, but also shading towards red. So what if I make this one brighter by adding a little bit to, and I'm going to rearrange these in a second. I actually like this one brighter. Let's add, what about, we need it to be brighter, but I also want it to make a little bit redder. So let's go full red, what we had for green, and a lowish amount of blue. And that's not too bad. Let's do that. And let's go like this. All right, there you go. That's not outstanding, but there you go. That does the trick. Okay. If you were trying to do the other ones, like this one, I would say make sure you're choosing a sampling frequency where it would do something. But at this point, this one really is only like 2 colors, purple and red, and I really think figuring out how to make custom colors is more useful, and the one I showed you is a little better for that. Okay, so go ahead and do that. And I think, yeah, the last 2 are checks for understanding. Let's take a look at them. And anytime you see on the assignment or due date situation, it says all bubbles. That means the bubbles for the assignment and the checks for understanding. And let's see what we got here. And okay, which of these statements about analog and digital images is true? Sampling analog more frequently produced. Okay, that's yep, pretty much what we've been talking about.